Hello. As a part of the science project, I am going to discuss Hermite polynomials, moment of inertia matrix, Laguerre polynomials, and dynamics of a rocket. Let's begin with Hermite polynomials. The Hermite polynomials are a set of orthogonal polynomials over the domain minus infinity to infinity with weighting function e power minus x square, and below it is illustrated for the values of n 1, 2, 3, and 4. It can be defined by the contour integral Hn of z equal to n factorial divided by 2 pi I contour integral of e power minus t square plus 2tz t power minus n minus 1 dt. The first 10 Hermite's polynomials are listed below. Now let's move on to the properties of Hermite's polynomials. Orthogonality. Hn of x are nth degree polynomials for n equal to 0, 1, 2 and so on. These polynomials are orthogonal with respect to the weight function e power minus x square. We have integral minus infinity to infinity hm of x into hn of x into e power minus x square dx equal to 0 for m not equal to n, or integral minus infinity to infinity hm of x hn of x e power minus x square dx equal to root pi 2 power n factorial delta nm. Completeness. The Hermite polynomials form an orthogonal basis of the Hilbert space of functions satisfying minus infinity to infinity integral mod of f of x whole square w of x dx less than infinity, in which the inner product is given by the integral including the function wx, which is the weighing function defined in the previous slide. An orthogonal basis for L2 is a complete orthogonal system. For an orthogonal system, completeness is equivalent to the fact that the zero function is the only function f which is in L2 orthogonal to all functions in the system. Recursion relation. The sequence of Hermite polynomials also satisfies the recursion h of n plus 1 of x equal to 2x hn of x minus h dash n x. Individual coefficients are related by the following recursion formula. A n plus 1 k equal to 2 a n k minus 1 minus k plus 1 into a n k plus 1 for k greater than 0. A n plus 1 k equal to minus a n k plus 1 for k equal to 0. The Hermite polynomials constitute an Apple sequence, i.e. they are a polynomial sequence satisfying the identity h dash n of x equal to 2n h minus 1 x. The Hermite polynomials are given by the exponential generating function e power 2xt minus t square equal to sigma n equal to 0 to infinity hn of x t power n by n factorial. Now let's move on to the applications. Hermite functions. Psi n of x equal to 2 power n factorial root pi power minus half e power minus x square by 2 hn of x equal to minus 1 power n 2 power n factorial root pi power minus half e power x square by 2 d power n dx power n e power minus x square. The Hermite functions satisfy the differential equation psi double dash n of x plus 2n plus 1 minus x square times psi of n x equal to 0. This equation is equivalent to the Schrödinger equation for a harmonic oscillator in quantum mechanics. So these functions are the eigenfunctions. CRAMÉR'S inequality. The Hermite functions satisfy the following bound due to Harald-Cramér for x real, where the constant k is less than 1.086435. Psi n of x less than equal to k pi power minus 1 by 4. Recursion relation. Psi n power m of x equal to sigma k equal to 0 to m mck minus 1 power k 2 power m minus k by 2 root of n factorial divided by n minus m plus k factorial times psi of n minus m plus k of x into he of k of x. This formula can be used in connection with the recurrence relations of hen and psi n to calculate any derivative of the Hermite functions efficiently. Hermite functions as eigenfunctions of the Fourier transform. The Hermite functions psi n of x are a set of eigenfunctions of the continuous Fourier transform. To see this, take the generating function and multiply by e power minus x square by 2. Finally, it would yield psi n power m of x equal to sigma k equal to 0 to m mck minus 1 power k 2 power m minus k by 2 root of n factorial divided by n minus m plus k factorial into psi of n minus m plus k of x times hk of x. F of e power minus x square by 2 hn of x equal to minus I power n e power minus k square by 2 hn of k. The Hermite functions psi n of x are thus an orthonormal basis of L2 which diagonalizes the Fourier transform operator. Now let's move on to the moment of inertia matrix. Consider a rigid body rotating with fixed angular velocity omega about an axis which passes through the origin. Let Ri be the position vector of the ith mass element whose mass is mi. We expect this position vector to precess about the axis of rotation which is parallel to omega. With angular velocity omega, it therefore follows dRi by dt equal to omega cross Ri. The figure is given below. Thus, the previous equation specifies the velocity Vi equal to dRi by dt of each mass element as the body rotates with fixed angular velocity about an omega axis passing through the origin. The total angular momentum of the body about the origin is written L equal to integral I1 to n MIRI cross DRI by dt equal to sigma I equal to 1 n MIRI cross omega cross RI equal to sigma MI RI square omega minus RI dot omega times RI. The above formula can be written as a matrix equation of the form as given below, where Ixx equal to integral I from 1 to n yi square plus zi square times mi equal to integral y square plus z square dm. Iyy equal to sigma I from 1 to n xi square plus zi square mi equal to integral x square plus z square dm. And similarly Izz equal to integral x square plus y square dm. Ixy equal to Iyx equal to minus sigma I from 1 to n xiyi times mi equal to minus integral xy dm. Iyz equal to Izy equal to minus integral yz times dm. Ixz equal to Izx equal to minus integral xz times dm. Here Ixx is called the moment of inertia about the x-axis, Iyy the moment of inertia about the y-axis, Ixy the xy product of inertia, Iyz the yz product of inertia, and so on. The matrix of the Ij values is known as the moment of inertia matrix. Each component of the moment of inertia matrix can be written as either a sum over separate mass elements or as an integral over infinitesimal mass elements. In the integrals, dm equal to rho dv, where rho is the mass density and dv a volume element. The equation can be written more succinctly as L equal to I tilde times omega. Here it is understood that L and omega are both column vectors, and I tilde is the matrix of the Ij values. Note that I tilde is a real symmetric matrix, that is Ij star equal to Ij and Iji equal to Iij, where star is the transpose. In general, the angular momentum vector L points in a different direction to the angular velocity vector omega. In other words, L is generally not parallel to omega. Now let's move on to Laguerre polynomials. Now let's talk about Laguerre polynomials. In the Sturm Louisville Boundary Value Problem, there is a special case called Laguerre's differential equation which arises in the treatment of the harmonic oscillator in quantum mechanics. In mathematics, for alpha greater than -1 and m, a non-negative integer, Laguerre's equation is the linear second-order differential equation x d square y by dx square plus 1 minus x dy by dx plus ny equal to 0. Its polynomial solutions, that is, the Laguerre polynomials, are used for solutions for the equation x y double dash x plus alpha plus 1 minus x y dash of x plus myx equal to 0. The first few Laguerre polynomials are as given below. The Rodriguez representation for Laguerre polynomials is ln of x equal to e power x by n factorial times d power n by dx power n times x power n e power minus x. ln power alpha of x equal to x power minus alpha e power x by n factorial d power n dx power n e power minus x power n plus alpha, which is equal to x power minus alpha times d by dx minus 1 power n divided by n factorial of x power n plus alpha. Their generating function is given as sigma n to infinity t power n ln power alpha of x equal to 1 by 1 minus t power alpha plus 1 times e power minus tx by 1 minus t. Their contour integral ln of z equal to 1 by 2 pi I contour integral of e power minus z t by 1 minus t divided by 1 minus t times t power n plus 1 dt. Recurrent relation for Laguerre's polynomial is n plus 1 times ln plus 1 of x equal to 2n plus 1 minus x times ln of x minus n ln minus 1 of x. X l dash of n of x equal to n ln of x minus n ln minus 1 of x. This graph shows the Laguerre polynomials with values of n from 0 to 5. Its closed form for degree n is given by ln power alpha of x equal to sigma I from 0 to n minus 1 power I n plus alpha c n minus I x power I by I factorial. In terms of Commerce transformation, ln power alpha of x n plus alpha c n m of minus n alpha plus 1 x. The constant term ln power alpha of 0 equal to n plus alpha c n, which is approximately equal to n power alpha divided by alpha plus 1. Asymptotic nature. Ln power alpha of x equal to n power alpha by 2 minus 1 by 4 times e power x by 2 divided by root pi x power alpha by 2 plus 1 by 4 cos of 2 root of nx minus pi by 2 of alpha plus half plus O of n power alpha by 2 minus 3 by 4. And ln power alpha of minus x equal to n plus 1 power alpha by 2 minus 1 by 4 times e power minus x by 2 divided by 2 root pi x power alpha by 2 plus 1 by 4 into e square root of x times n plus 1 times 1 plus O of 1 by 1 root of n plus 1. According to Forward's theorem, the Laguerre polynomials thus form a family of orthogonal polynomials. The orthogonalizing measure mu of the Laguerre polynomials is given by d mu of x equal to x power alpha e power minus x dx. The orthogonality with respect to the Laguerre measure mu may be proved as follows. The Laguerre's equation is equivalent to the statement that L, the eigenfunction with eigenvalue m with respect to alpha of the second order differential operator L equal to minus x d square by dx square plus x minus alpha minus 1 d by dx. The operator L is self-adjoint with respect to the inner product fg equal to integral 0 to infinity f of x g of x d mu of x. Other types of Laguerre polynomials. The Q-Laguerre polynomials are a discrete or quantum variant of the classic Laguerre polynomials. They were first studied by Hahn around the 1950s. The Q-T Laguerre polynomials are for the evaluation of multidimensional integrals related to Lie algebras. Now let's talk about Lagrangian and Hamiltonian rocket dynamics. Lagrangian. The equation of motion of a point mass rocket in Lagrangian form, valid in any coordinate system, can be derived by considering the 3D orientation of the rocket. The Lagrangian form of the rocket equation is used for calculating rocket motion, which can involve complicated constraints. Here, the use of generalized dynamic coordinates is advantageous. We consider the rocket a point of variable mass moving with velocity xi dash in any direction where I equal to 1, 2, 3. mxi dash equal to mci plus fi, where m is mass of the rocket at instant t and x is the velocity of expelled mass relative to the rocket. Differentiating on both sides, d by dt of mxi dash equal to m dash ui plus fi, where ui equal to xi dash plus ci and is the absolute velocity of expelled mass in the fixed coordinate system. Here, xi is a function of qa and t when we generalize where a equal to 1, 2, 3, 4 and so on till n, where n is the number of degrees of freedom of the rocket. Kinetic energy of the rocket at instant t is half mt x1 dash xi dash. Now by partial differentiating dy dt of m xi dash equal to m dash ui plus fi, we get dy dt dt by dq dash a minus dt by dq dash a equal to m dash ui dxi by dqa plus fi dxi by dqa, where x1 equal to r sin x cos omega t, x2 equal to r sin x sin omega t plus and x3 equal to r cos x, where r is the distance from origin to the rocket, x is the angle it makes with x3 axis, that is the z axis, and omega is the angular speed of the rocket, where we consider a straight line describes a circular right circular cone where omega is along x2 axis. Hamiltonian. Similarly as done in Lagrangian, we can calculate the Hamiltonian by using the expressions h equal to k plus u and q dot equal to dou h by dou p and p dot equal to minus dou h by dou q. By solving the above equations, we are able to describe the dynamics of a rocket similar to how we did so in case of Lagrangian dynamics. We'll finally arrive at the same answer.